All right, let's get right into it. Today, we're looking at a pretty incredible new idea, a proposal that wants to expand on one of the most fundamental concepts in all of physics, the principle of least action. It's called the harmonic quantum action law, and you know what? It just might be the key to cracking some of the universe's deepest mysteries.
But here's the kicker, the thing that makes this story just so amazing. This whole ambitious new idea wasn't developed over decades by a team of tenured professors. Nope, it was proposed by a 17-year-old independent researcher. This is where you see cutting-edge physics meet a truly remarkable human story.
So, who exactly is the mind behind all this? Let's take a second to introduce this new voice in physics.
So, meet Prosper Chanda. He's just 17 years old, and he's already working as an independent researcher. And get this, his affiliations include the World Research Fellows of London and the African Materials Research Society. And he's also a prospective student at Northwestern Polytechnical University in China. I mean, wow, that's the background he's bringing to the table to tackle some of the biggest problems out there.
So what are these huge problems he's tackling? Why do we even need a new theory in the first place? Well, it turns out, for as much as we think we know about the universe, there are some major glaring holes in the picture. The universe has some missing pieces. And this quote from his paper just nails the motivation. Our current models in physics are built on things called Lagrangians. You can think of them as the mathematical DNA that dictates how everything works. And they're incredibly successful, but they don't explain everything we see out there. It's like the universe is whispering to us, hinting that there are these subtle, weak forces at play that our current rulebook just doesn't account for. And we're not talking about minor little details here. We're talking about the absolute biggest questions in all of cosmology. Things like, why do galaxies spin way faster than they should? What is dark matter and dark energy? The stuff that makes up 95% of everything. And why is there this weird energy in totally empty space? These are the giant gaps this new theory wants to fill.
Okay, so how does the harmonic quantum action law try to do this? Well, the beauty of it is really in its simplicity. It's not about throwing away centuries of physics. It's about adding a new, subtle layer, almost like listening for a quiet, harmonic hum that's been in the background of the universe all along.
Now, to get the new part, you first have to understand the classic idea it's built on, the principle of least action. It's such a cool concept. Imagine a lifeguard on a beach who sees someone drowning. Does she run in a perfect straight line? No, she runs along the sand for a bit and then jumps in the water because she can run way faster than she can swim. She instinctively finds the path that takes the least amount of time. Well, the universe does that too, always picking the path of least action.
So, here it is. This is the heart of the idea. On the left, you've got the standard equation, that L0. That's all the physics we know and love. But on the right, Prosper Chanda adds one simple, elegant little thing. A new term, kappa H. That single addition is designed to be the placeholder for all those weak, hidden forces we've been trying to find.
Let's break that down using an analogy because it really helps. Imagine that L0 is the ocean with all the currents and tides we already know about. This new term, kappa H, is like discovering a totally new unseen current. Kappa is like its strength. Is it a gentle little push or a powerful pull? And H, well, that's the nature of the current itself. Is it a steady flow? Or does it have a kind of rhythmic harmonic pulse to it? That's the hum we're talking about. This is all really cool in theory, right? But the most important question for any new scientific idea is pretty simple. How do we actually test it? I mean, how would you even go about detecting a hidden force like this? Well, it turns out the theory gives us some specific clues to look for. You see, the strength of a good theory is that it doesn't just explain things, it makes predictions you can actually measure. And this one does. It says we should be able to see tiny, tiny deviations in the paths particles take, or small shifts in how fast things vibrate. And, crucially, we might see noticeable shifts in certain quantum experiments. These effects could be super small on their own, but in big systems they could really add up. Let's make this super concrete. Think about the classic double-slit experiment in quantum mechanics. Standard physics tells us that when we shoot particles through two slits, they act like waves and create a really clear interference pattern on the other side. You know, a series of bright and dark stripes.
But here's the twist. The harmonic law predicts that this hidden hum, this extra interaction, would actually nudge that pattern ever so slightly. It would cause a tiny but measurable shift. Finding that shift? Well, that would be the smoking gun. The proof that this unseen influence is actually real. So, with the testable prediction in our back pocket, where does this research go from here?
This isn't just a cool idea to think about, it's the start of a real scientific investigation with a clear path forward.
And there's a whole roadmap laid out. The next steps are to dig even deeper into the theory itself, then run computer simulations to see how its predictions stack up against real-world data from both laboratories and telescopes. And from there, you'd expand the whole framework to work with bigger ideas like relativity. It's a very logical, step-by-step plan.
And this is a really important point to stress. This theory doesn't come in and break physics. It actually builds on it. It keeps the core structure of everything we already know intact, while giving us this brand new, controlled way to go looking for those mysterious weak influences that have had scientists scratching their heads for decades.
And at the end of the day, that's what's so powerful here. It gives us a consistent, a mathematically solid, and, this is the most important part, a testable way to move forward. It's a brand new tool for scientists to use in their hunt for answers.
Which leaves us with this one last really provocative thought. Could it be that the answers to the biggest mysteries in the cosmos, dark matter, dark energy, aren't hiding in some violent, high-energy particle collision, but instead in the quietest, most subtle hum of the universe that we just haven't learned how to listen for yet?
And that's really the spirit of this research. It's an open invitation. It's a call to the entire scientific community for discussion, for collaboration, for mentorship. It's a powerful reminder that science is a journey, not a destination, and this is just the first step on a very, very exciting new path.